Alright folks, welcome back. Tonight we're going to be going over section 10.5, partial pressures. Alright, now let me tell you about partial pressures. In a mixture, you have gases, especially if the mixture is a gas that you're dealing with, and there's a bunch of individual gases in there. And then you can take all these individual gases with their individual pressures and add them up and get the total pressure. The total pressure. Alright, now one of these laws that we're going to be discussing is Dalton's law of partial pressures. Basically what I just stated, the pressure of individual gases can sum up and give you a total pressure. Now, one common way of collecting a gas is over water. Basically, you take a reaction involving possibly a metal and an acid, and you have them to react, and you get the desired gas that you're trying to produce, and you're able to collect the gas into a container, usually a test tube or a bottle of some sort that's been filled with water, and as the gas goes in to the top, it pushes the water out to the bottom. So basically what this does is it allows you to see how much gas you're collecting, but the problem with that is as the gas is coming to the top of the water level, it's basically throwing water up into the gas with it, meaning when the bubble pops, it allows water vapor to go into the air along with the gas that you're trying to obtain, and you get what is known as a wet gas, which you can see here from the drawing. Alright, now, and here is the gas collection over water. Just remember, you take the total pressure and you subtract the pressure of the water vapor, and this is all due to whatever the current temperature is outside. So just read over this, and you can pause the video and do that. Now, here is a table of that we'll use for the problem that we're about to do, and with this table you use this to find out how much you need to subtract from the gas that you obtained. Okay. Anyway, let's go ahead and get started with this. Now, here is our problem. Okay. Alright guys, let's go ahead and get started. I'm having to do a correction to this video because when I did the original video, I did it for 25 degrees Celsius. I have no idea why. And also in the original video, I didn't pay attention and I just did it for torr. I didn't even go to millimeters of mercury. So I apologize. So that's why I'm re-editing this problem. Alright, let's go ahead and get started with this. Here, what we need to do is we need to understand what's going on. We have a wet gas. Basically, the simplest way to collect a gas that you've made is to collect it underwater. That way the gas that's bubbling up is the gas that you're finding. The only problem with that is you're getting a wet gas, and meaning as the gas molecule is coming up and it breaks the surface of the water, in this case the liquid is also clinging on to your gas, so you get this water vapor going up with your gas. So you just don't have your pure gas. You have what's known as a wet gas. So basically, since they're wanting us to basically find the vapor pressure of oxygen here, of oxygen gas, then this is what we in a sense have. We have the partial pressure of O2 equaling the partial pressure of the wet gas of O2. So basically we have O2 that has the little car rider of water with it going up into the air. And the problem with that is we are truly not getting the partial pressure of oxygen. We're getting it for the wet gas of oxygen. Okay, so what we need to do is we need to subtract that off. So we'll subtract off the partial pressure of water. Okay, so this is essentially what's going on. Okay, now they gave us some numbers, and they didn't tell us the partial pressure of O2, but they did tell us the partial pressure of the wet gas O2. And I know this because when I was doing the reading, it said that the sample of oxygen is collected over water. Okay, that means it's going under the water then rising up. And they gave me a temperature and they gave me a pressure. So the pressure that this gas was collected over was 738. So that's the pressure of this right here, 738. Now there's a problem. I have no idea of the partial pressure of water. So I'm going to have to look it up for water at 20 degrees Celsius. Now in my notes, I included one for my students here. Here's the temperature of 20 degrees, and I need to use the 17.54 because that's the vapor pressure in torr. So let's go ahead and grab it real quick. Okay. Whoops, that's the video. Alright, so subtract. I need to finish editing. Subtract. Now, what was that number? I forgot it already. 17.54. Okay, so 17.54. And that's torr. Okay. Now, we will need a calculator to do this. Oh, sorry for the ugly P there. Let me see if I can try to redo that. Okay, partial pressure of O2, which is oxygen gas. Remember, oxygen is diatomic, that's why it's O2. I subtract these two numbers and turn on the calculator. And I did this earlier, and 738 minus 17.54 torr is 720.46. So let's go ahead and key that in. 720 point, what was it again? 46? Yeah, 0.46. Now, that's the incorrect number of sig figs. Okay, so I need to correct that. I am not going to leave it 720.46, so I'm going to erase this answer and just write 720 because there's only 3 sig figs. Remember, in addition, you keep the least amount of numbers behind the decimal, and in this case we don't have any numbers behind the decimal in this one, so the answer is 720. 720 what? Torr. Well, the direction said it wanted it to be in millimeters of mercury. Well, that's an easy conversion because 1 torr is equal to 1 millimeter of mercury, so the partial pressure of O2 is the same number again, 720. We're just going to change the units. 720 millimeters M Hg. Okay. Now that one is finished, and technically we've answered everything that the problem has asked us to do, but there is one more thing that I would want to show you. If they did want you to convert this into ATMs, okay, if they wanted ATMs, what you would need to do is do the following. Set up a dimensional analysis, put the 720 mm sorry, I think that's too many M's there, but anyway, Hg, and put it over 1. I come over here and then put this for 760 mm, one more hump I guess, Hg is 1 ATM. You know, ATM, atmospheric pressures. Okay. Anyway, we would divide those two. Notice that we only have 2 sig figs. So let's go ahead and punch that into the calculator. We have 720 divided by 760. So we'd only keep 2 sig figs. So our answer would be 0.95. 0.95 ATMs. Now that's if the problem asks you to go to ATMs, and I wanted to make sure to show that. So because it's an easy conversion that we should all be able to do. But anyway, this is the correct answer, so I hope that the video was helpful, and just watch it over. And I'm sorry for the earlier video being incorrect because I had used 25 degrees Celsius instead of 20, and I just left it in torr and then talked about converting it to ATMs. But this time I believe I have fixed it for you. Alright, hope it helps, guys.